Okay. So yesterday we talked about what is a machine learning and how is it different from, I don't know, let's say traditional programming. And we had some, I don't know, some bite of machine learning when we tried to do linear regression. And today I want to proceed a little bit with linear regression, just say a few words about one particular example that I want to present in terms of linear regression, because that is the machine learning method that we already know. And let's check how it plays. So what I want to show you is called regularization. I have already told you that we have a method of some sort of constraining parameters inside of our model. So what was machine learning? We were building an algorithm that has some internal free parameters, and these free parameters are chosen based on some different algorithm that was basically performing the training. And when we were performing training, we saw that we may have some problems. Which were the problems? So the first problem, our model might be too stiff. It has too low number of parameters, and we need to make our model a bit more flexible. That was basically that was still okay. Why? Because we see that we have problem when we are training our model on the training set, but we have a different problem when our model is too flexible. That's when that is the case when we don't see any problems when we perform training, but on a validation set, we see that model performs quite poorly. So what do we want to do now? We want to avoid somehow this overfitting. So we want to make our model a bit less flexible. To make it a bit less flexible, we can, of course, try to throw away some parameters, but in some cases that might be not very good for us, or we don't want to throw some parameters out of the model. So what we want to do, we want to constrain them. That will make our model a bit less flexible, and and that is a possibility for us to avoid overfitting. But that is not throwing away the whole parameter, it's just constraining it. So for example, it could be a number from minus to plus infinity, and we are constraining it, let's say from 0 to 1 or something like that. Let's take a small example and look how it works on example of linear regression. So here is one interesting case I want to show you. As I told you before, linear regression has the word linear not because it fits with straight lines. No, it's because this is a way of considering of linear combinations of some basis functions. So here is the case when we are considering as basis functions some Gaussian functions. It may be not, let's say, the brightest idea, but basically it still works more or less. So I have a bunch of functions of this form, one here, one here, one here, and so on. I'm basically multiplying them with some quotients and adding together. So I multiply them by some K1, K2, and so on. And I'm adding everything together. Just a simple linear combination, nothing more. At the end of the day, I get some approximation of my points that basically were input to my linear regression. Depending on how many of these basis functions I take and how do I allow their parameters to change, I may get different results. Whatever you see right now is a classical example of heavily overfitting. So as you see, our curve perfectly gets through every point, but you may guess that it's not what we want to get as the result. As a result, we want basically get something like more like this, but not what we have right now. So what can we do? We can employ the process of regularization. How and why? First of all, let's check what happens to the quotients that we have, this K1, K2, that we were multiplying with our basis functions. Let's see what happens. We see that these quotients, they are changing they are very heavily changing. You can see here 500,000 plus and 500,000 minus. So they are really big. They are changing their sign. And we may think that, hey, it's somehow wrong. Why are we adding our basis function with such large quotients? Our points were leaving basically from, I don't know, +1 to -1. They are not so heavily scattered around the plane. So why do we have such large quotients? So the first thing we might think that we may somehow constrain these quotients, and maybe that will help us to get some more reasonable curve as the result of our fitting. So that's basically the idea. How do we restrict these things? First of all, I told you that every machine learning method is basically minimization or maximization of something. In case of linear regression, we had an exact function that we called SSE that we should minimize to get our result. Well, basically, minimization of SSE got us here. So it's not very good result. What we want now, we want to add some constraints and say, yes, I want to minimize SSE, but I have constraints. I want my quotients not exceed some predefined value. I don't want them to be too big or something like that. How do we do that? Basically, constraints are added to the function that we minimize when we are constructing so-called Lagrangian. I'm not sure if I have enough time to get into details, but what I want to show you, if this is the function in color that you minimize, and these are, I don't know, some field of, let's say, constraints that you are using. By constraints, I mean that you have some function and you are saying, I want this function to be less than 0, for example. That's pretty okay. That's pretty standard case of constraints. I want it to be less than 0. Of course, you might come up with the idea, how do you present our demand that our quotients are less than a certain value in terms of some functions that should be less than 0. That's a pretty simple thing. What do we do now? You see that inside this black, I don't know, it's not a circle, let's say ellipse, or how does it look like to you? Our function is really less than 0. Here we can take any point, and this point is feasible. So it means that constraints are satisfied. We cannot take any point outside because constraints are not satisfied and we don't want that. Now, among these points, we should find the point that has the minimum value of the SSE. In here, you see some sort of physical representation. SSE is pulling this particle towards its minimum. So this particle is trying to get a minimal potential energy, and potential energy is basically expressed as the function that we should have to minimize before. And this is, and this black thing, you can think about it as a wall. The particle can't get through the wall. The wall is stopping, is preventing the particle from getting to the minimum of, to the possible minimum of the potential energy. But it's still getting some minimum, considering that it can't pass through the wall. And as you see here, gradients of the pulling potential that you were trying to minimize, and gradient of the function that is defining your constraints, they are on a perfect straight line. And it's always the case. Why? Because if they are not on a straight line, you can see that you have some additional force that pulls the particle somewhere to the left or to the right, depending on where you are. Well, this is basically one of the so known conditions of KKT, Karush-Kuhn-Tucker, and well, I don't have too much time to get too deeply into details, but how it plays off, you get this sort of equation. It's basically saying that these gradients are on one and the same straight line, and at the end of the day, combining everything together, you get an expression called Lagrangian. And it seems that you can solve your initial problem that you had of minimization with some additional constraints by basically finding the minimum of this new function, of this Lagrangian. And it differs from the initial function f of x just by adding some new summands, something new that basically defines your constraints. So that's how it works. Now, what do we do with linear regression? Why am I talking about all of this? I want to constrain my vector of parameters w. So I want all these parameters to be less than some predefined value, let's say r. So I'm saying I have a vector of parameters w that basically define the quotients that I used in my linear regression when I was adding all that basis functions. Okay, this is my constraint. So this constraint can be added to my initial SSE I was working with, so to my initial energy, to get some sort of Lagrangian. This is my Lagrangian that I should minimize. And this is a parameter alpha that I'm multiplying by all this stuff that basically defines me the strength of the regularization. If alpha is equal to 0, I'm basically getting just a simple linear regression. If alpha is very large, I have a strong regularization, and depending on, on the case, for example, in this case, this is so-called L2 regularization, I will get, basically, I will force all my quotients to be equal to 0, and I wouldn't get anything meaningful. So I should choose this alpha somehow wisely. So how do I choose it wisely? Well, I can perform testing or some sort of cross-validation of my machine learning algorithm. And if I see it's overfitting, okay, I'm increasing alpha. Still overfitting, still increasing. Stops overfitting, oh, that's great. I found my perfect value of alpha. Okay, how it works, let's see. So this is called also reach regression. So you might hear both terms. So L2 regularization, reach regression, something like that. Or Tikhonov regularization, that's all interchangeable terms. So what do we have here? This is our field that basically grows the particle to the minimum. This W1 and W2 are two values of parameters, are perfect values when you do just simple linear regression. This is our constraint. We say that I don't want my parameters W1 and W2 to get out of this circle. So, so I want to constrain it. And here is basically the point when I get minimal, let's say, energy that still satisfies my constraints. So it means I have regularized my regression and I got some result with parameters constraint. Okay, how it works? Let's see on a practical example. When I perform reach regression, as you see, here is my parameter alpha. I set it to 0.1. Just because I set it this way, so maybe there is some better choice. But anyway, as you see, the curve I'm getting from fitting is much better than what I had previously. And these are parameters. As you see, these parameters are heavily constrained. There is no more 500,000. There is no more minus 500,000. They are heavily constrained from, I don't know, 0.3 to minus 0.4. And this what we had. This was what we had previously. So definitely a heavy overfit, in contrast to something much better. One more way to make constraints. Here I have an example that I want to show you. What happens to reach regression when I increase this parameter alpha? You may see right now alpha is 0, and what you get perfectly coincides with simple regression. When I increase the strength of the regularization, my parameters are getting smaller and smaller. Well, basically in this case, I'm having almost one parameter. This parameter defines the slope of the line, and you see that this slope is getting more, you're getting the line more and more down, so the slope gets to 0. what is actually expected because we are demanding basically from our parameters to be smaller and smaller. Okay, there is another case that we will use in a different example. I will tell you a little bit later about support vector machines, and we will use so-called Lasso regularization or L1 regularization. Basically, the same thing, but if I was taking the whole vector of parameters W, and I was demanding for this vector for its length to be smaller than some predefined value R, right now I want a sum of absolute values of each parameter W to be less than R. It may seem quite similar, and you might think, well, it's different from the previous example. But actually it is. It is quite different. That's what interesting. We have a new function to minimize. It's once again, it's SSE, so the function that we had, plus some additional thing. This additional thing is basically sum of absolute values multiplied by some parameter alpha, and this parameter alpha once again defines the strength of our regularization. So tuning this alpha, I can get my parameters more or less constrained. Now, what's different? There's one interesting thing that is different. I just want to show it, I don't know, as some intuitive example, so without getting to some mathematical details. As you see, here is my minimizing field, as I call it. So this is the initial function SSE, and here is the point you will get to if you minimize without any constraints. This is my field of constraints. Right now, it looks this way. So you might think of it like, I don't know, some spheres in Manhattan metric, or basically just think about how this function with absolute values look like when you have, I don't know, absolute value W1 plus W2 is equal to some sort of constant. So you get just this straight lines. Here is the best point. So this looks quite innocent, but there is a chance that you can get a touch between this sort of Manhattan sphere and your minimizing field somewhere in the corner. And this is very interesting because if you have a touch in the corner, it means that your parameter, one of your parameters or few of them, are basically equal to 0. In this example, you see that W2 is right now is equal to 0. It's not close to 0. It's definitely equal to it. So it's a straight 0. What it means that you basically throw away one feature from considering. Why is this interesting? It's interesting because you can use this method. You can, in this way, you can basically remove some redundant features. So you are doing regularization. You are constraining your parameters. But with L1 regularization, you can get some insights and get the idea that some features are basically introducing nothing interesting to your model, or they are just introducing some noise. So that's the interesting part. So you can nullify their quotients. And the end of the day, if you examine what are the values of that quotients, of that K1, K2, so on, that you had when combining or all that basis functions, you may get the idea, there is something interesting. Some features are redundant. I may remove them, and it will be even better for my model. Okay, how it looks in practice. Once again, we have the same linear regression with the same points. And once again, you see that there is no more heavily overfitting as we had at the beginning. What happens to the quotients? Let's check them out. Here are the quotients. Once again, they are smaller. That's okay. So we have somehow constrained them. Moreover, you can see that some quotients right now are basically lying on 0. Let's say these two quotients, this one, these two, and so on. So we have basically thrown away part of our basis functions, and that's interesting. That may be helpful. Here how it looks like when you are increasing strengths of your alpha. When alpha is close to 0, you basically get to the same simple regression, nothing fancy. When you are increasing strengths, once again, you see that the slope is changing and the line is getting more and more closer to being horizontal. Moreover, when you get through certain threshold, you will get your quotient nullified and it perfectly lies and becomes horizontal. You haven't seen this effect on my previous demo. There, I can increase strength of my alpha, and this line will get more closer and closer and closer to being horizontal, but it will never get horizontal. There'll always be some value of parameter that parameter k that we use in our linear regression. But here, there is some sort of threshold. When you get to horizontal line, it becomes perfect 0, and nothing changes later if you increase strength of alpha. That's an interesting point. Here's one more example. This is reach and lasso regularization. Here you see the minimizing field I'm right now tuning. It's shown in color. And what you see as the green line, it's some sort of trajectory of a particle that it will move if you increase the strength of regularization. So here I am increasing the strength, and you see how the blue dot moves. So where do we get our minimum, considering constraints and considering our SSE? Now let me move to lasso regularization. And as you see right now, our particle at some strength, at some value of alpha, gets to this x-axis, becomes 0, and nothing more changes. Okay, so since we don't have much time, I just encourage you to play with this demo after the lecture. I have a 3D here, but it works a little bit slowly, so I'm a bit of hesitant to start it here. Okay, here are the paths of quotients that we used previously. So here we see that reach quotients as function of alpha are just all together getting more and more smaller. And here is lasso coefficient that you may see that they are getting to 0 and staying 0 for some time. It may happen that they get to 0, stay 0, and then get out of 0. That's possible, and you can even reproduce that in this example. But unfortunately, I don't have, we are really scarce on time to show that. Okay, and here is one more idea that may come up to your mind. So if we have two such nice regularization, why don't we combine them in something altogether, and we can get so-called elastic net. So this is a combination of L1 and L2 regularization. And you have one more additional parameter called L1 ratio that basically depends, are you regularizing more like L2 or more like L1? Okay. With that being said, I think we are more or less clear with this idea of regularization. And I think we are ready to get to our next topic I want to show you. And we will use this idea, we will once more use it for another machine learning method called support vector machines. Okay, so I know it's a bit of a rapid switch, but we just need that ideas of regularization to make basically sense of some equations that define support vector machines. First of all, let me show you how it looks like. So we were talking previously about the problem of regression. So we were doing regression. What it means that that was supervised learning, and we had some not discrete, some continuous classes. So you get at the result some real number, for example. When we are doing classification, that's the problem we will consider now. We will have discrete classes. So there is a discrete number of classes. Okay, so let me first show you how a support vector machine looks like, and then we get to more details. First of all, what is this picture? So this picture is basically our data set. Right now, I'll be putting some points into this data set. So what we have, X and Y axis, these are two features. So this is, let's call it feature 1. X-axis, you may call it feature 2. So these are two features. When I am setting some point on this field, I'm basically defining a data point. So my data points will be collection of two features. Each feature is some real number. Data points have colors. These colors basically define classes. So so blue data points, they belong to the blue class. Red data points, they belong to the red class. So that's okay. We have a discrete number of classes, as you see, blue class, red class, so on. Well, actually, support vector machines are binary classifiers, so it takes you a little bit of work to get them to work with more classes than two. So that's that's a little bit of a problem. Just to mention, I think. Maybe we will get to that later, maybe not. So just know that there is some sort of problem with that. Okay, so what do we have now? Now we see that field has two colors, red and blue. What it means? This means basically what this machine will answer when you ask it to which class you should give to the point. Let's say this one. Bad choice of color. Let's say this one. So you are asking, okay, classify me this point. And it says you, it's class blue. Classify me this point, it's class red. Or this point, it's still class red. So this is a classifier, binary classifier. Okay. What can it, how does it classify? Well, what you see now is support vector machine with so-called linear kernel. It draws a straight line that should somehow separate red class from blue class. We will get into details just a little bit later. I just wanted you to show something to get you some sort of intuition what SVM are capable of. So it's trying to draw a line that separates these points. But basically, it can work with cases when you cannot separate your points. So for example, if I get some red point right here, it will still find some line that more or less separates blue and red classes. Moreover, what we will need so-called kerneled support vector machine with using kernels. And when you use kernels, it is capable of drawing not only straight lines, but something more, much more complicated. As you see in this picture, it's a really complicated borderline between red and blue classes. And moreover, they are perfectly separated, as you might see. Let me take some point and, I don't know, move it around. As you see, there's a really, really complicated borderline. What else can you see? As you see here, there are some points that I have highlighted with a small yellow dot. These are so-called support vectors. These points are basically special in this situation. They are basically defining this borderline. I will show you formulas a bit later if we will have time, but I just want you to give some intuition. So some points are basically much more, let's say, useful than other points. When I move any point here, nothing changes. So nothing will change. They are not support vectors. So when I move them, nothing will change. But when I move a support vector, you see that the picture changes. When I get this point here, it becomes a new support vector, and this one stops being support vector, so I can still freely move it around and nothing will change. So basically what you see here is a live work of a support vector machine. And this is what we'll try to get in a form of equations. Okay, now let's get through everything this. So how do we pose a problem? So let's start with a simple problem. We have two classes, once again, now yellow and red. And we call these two classes linearly separable. Why? Because I can draw a line that basically separates these two classes. And I want to pose the problem of finding the best line that will separate these classes. Of course, you might ask me, well, there are many lines that separate these two classes, yellow and red. Which one do we have to choose? And it seems quite reasonable to find the line that lies as far as possible from both classes. So you see here around these lines, I have drawn some sort of streets. So I made them thick as possible. And they are touching some of these points. So every line is touching a yellow point on its, let's call it right side, and a red point on whatever I should call left side. So these are some sort of streets. And I want some algorithm that will maximize the width of this street. Okay, of course, you may ask me, how do I see that this is a machine learning method? What's happening? First of all, how did we define machine learning methods? These are some sort of programs with free internal parameters that we will fill in when we perform training. Internal parameters for this algorithm are basically, once again, parameters of the straight line. But in the case of linear regression, we have the straight line to pass through the points. Right now, we demand this line to separate some sets of points. Okay, so we have three parameters. How do we classify if we have these parameters? So for example, let's say we have some algorithms that will give us these parameters, but how do we work with that? And the interesting thing is that you can define straight lines in terms of some vector. Let's say it's my, I know, x is x and y. I have a straight line here, and I can draw some vector perpendicular to this line. I can write the equation of this line in the following form. So I have this line. I can write that each point that I scalarly multiply by this vector w, what I get when I'm performing this multiplication, I'm basically projecting it on the direction defined by w. Let's say for a moment that norm of w is equal to 1. So just to make things easier, I have some sort of projection. So here is my projection. And it seems that this projection is equal to some sort of constant for each point that lies on this line. So it is equal to some, I don't know, let's go with b, whatever. So all points that are lying on this line, they should satisfy this equation. But what is interesting now? Well, basically all points lying to the left of this line and lying to the right of this line, they can be distinguished. How? Some of them, when I'm multiplying x, let's say right point times w, will give me values that are less than b, while other points, let's call them left times w, will give me something that is bigger than B. So that's what we have. So basically, we can calculate something like this. So I just perform a scalar multiplication. I add or subtract whatever, some constant, and I get a number. And a sign of this number, whether it's positive or negative, will define me to which class I should think my point belongs to. So that's the case. So this is basically how do we do a classification in case of linearly separable sets. Okay. What we do now? Well, now we do some sort of mathematical transformation. Once again, we are too scarce in time to get you through all of this, but maybe you will believe me that all this math works. But at the end of the day, what you get? That you can perform a minimization of your vector of parameters W. Basically, we use W norm of W. You should minimize, but we use norm of W squared to make things easier. And you have some sort of restrictions. These are our constraints. These are our constraints. Okay, as you see in these equations, so what do we have? We are basically probing our points from data set. They are all indexed with I, so they have coordinates xi. We are multiplying them by parameters w. We are adding that constant. So basically, sign of this thing should define to which class they belong, or at least our machine thinks they belong to. And interesting thing is that I am multiplying it by y indexed y. It is the value to which class they should belong. And you might see that if the class is +1 and it is a true positive, let's say, yeah, and thus yi is +1 as well, they are multiplied and you get something positive. If it is negative, it is smaller than 0, and yi is as well equal to -1, so our machine guessed correctly. We have negative times negative, we still have some positive value. So you may somehow believe me that when you are calculating this thing, you should always get something bigger or equal than +1. +1 we got because we performed some sort of normalization by the width of the street we are working with. So that's basically the case. So what do we have? We have some function to minimize, and we have constraints. So that's what I showed you previously. How do we work with that? We basically construct a Lagrangian, and we minimize that Lagrangian. So that's what happens. Okay, what are the results? Here is an example of what we are doing, and it shows you basically why support vector machines are still used and why are they so good. You see a very small data set, just 10 points. I am performing this SVM, and here is the line of separation between these two sets or two classes. Everything above this line will belong to the red class, and if you ask it to classify some point, it will tell it's red. Everything below will belong to yellow class. Now what happens when I get to 60 points? The line slightly changes. Not very, but slightly changes. Why? Because we have new support vectors. Once again, what was basically crucial for support vector machine? So we were demanding to get the most of the most widths of the thread that we were trying to build. How this width is defined? It's basically the distance to the closest points from these sets, from the red set and from the yellow set. This closest distance to this, the points to which we get this closest distance are called basically support vectors. So they support our street. Here they are shown with these blue circles in these images. When you add, when you change something, when you change some points that are not support vectors, nothing changes. So result of your support vector machine does not change if you do something with some vectors that are not support vectors. Now what happened here? I added 50 points to these 10 points. So some of them got closer to this line. This means that we obtained new support vectors, and that's why the line changed. Okay, but what happens when I add more? Let's say I make 120 points, and you see that anything barely changed. So I almost got my perfect support vectors when just having 60 points, and when adding more points, almost nothing changes. So the line barely changes. The same happens when you make 200 points, and so on and so forth. So adding more and more points changes almost nothing. Why is it good? This means that support vector machines are good when working with small data sets. It's really an often case that you have some small data set and you don't want to use a neural network on it. You will get a heavily overfitting. But you can still use support vector machine, and it may provide you with good enough results. Okay, I think we have 10 more minutes. Yeah. Okay, let's get it quite quickly through. Okay, so that was a case of linearly separable sets. What happens when they are not linearly separable? We change a little bit our math, and we allow points to get behind this line of separation. Okay, so we rewrite our formulas, and we allow each point to make through this line for some distance psi I. That would be good, but you might think that if I allow every point to get through that line for some distance psi I, why don't they all just wander around and mess my support vector machine? And whatever helps me in this situation is regularization. So less so regularization, L1 regularization that I told you. What I want is to make these points not go, I want a minimal number of points to be allowed to pass through this line. So I want just a minimal bare minimal number of these points. I don't want all points to wander around and do what they want. No, I want to constrain them. And here is the place where L1 regularization that I showed you will help me. So I can allow every point to wander around, and I add this psi I, but I include a regularization that will suppress this psi I and will make most of them equal to 0, which means that most of points will behave as previously, and only some of them will be allowed to pass through the border between classes. What do I get as the result? Here is an example. So here is example with this sort of regularization and so on. So what do we have? Once more, I have strengths of regularization. Previously, we called it alpha. Here in SVM, it's called C for some reasons, but that's the way this variable is defined in sklearn library, so I prefer stick to it. And here we have C equal to 10. We are heavily regularizing. What it means, a heavy regularization will demand that parameter psi are almost all equal to 0, and we will make our points to sit where they are. We don't allow them to cross the border somehow. So here you see just support vector machine working as previously. When I make this strength smaller, let's say C equals to 0.1, I allow my points to get closer to this borderline. Some even may cross to the other side. That would be still okay if you make regularization small enough. So that will make my border passable. So I can move through. I can let points to get through this border. Okay, there is one more example of how that works, but once again, we have no time to get through it, so I encourage you to look materials of the lecture later and start this sort of example and just play around with support vector machine and see how that plays out. Okay, and the last thing I want to show you is the kernel SVM. So what we do now, the problem we have posed is defining a minimum of some sort of Lagrangian L. I showed you in previous lectures, well, basically how it works. It's called the primal problem. This problem can be formally written as infimum of supremum. It's like minimum of maximum of Lagrangian. Maximum is taken with respect to that additional parameters mu and lambda that you have, while minimum is taken with respect to parameters of support vector machine. We can switch them places and take maximum of minimum, and we get so-called dual problem. There is no warranty that this dual problem will give you the same result that your primal problem gives you. It needs something additional. But in case of support vector machines, it plays out that it does. It plays so that it gives you the same result. So we can switch to the dual problem. I'm not getting you through all these formulas. You just perform that switching, you find that minimum, so on and so forth. So at the end of the day, you get just another form of Lagrangian. What it gets you to, it gets you a new form of Lagrangian that contains only scalar multiplications of vectors of your data points. And this is really good. Why? Because here comes the so-called kernel trick. When you calculate this Lagrangian, you can switch your space from the space you were working in to some another space. Maybe it has more dimensions, maybe something else. And if in this space your sets were inseparable, let's look at this set. You can separate that with a straight line. That's impossible. But when you get to the 3D, let's look at this space. You can place these points, you can endow them with some third coordinate. Here it is equal to x squared plus y squared. And you see that it becomes linearly separable. You can draw a plane that separates these points. And this is very crucial. The most interesting thing that you only need to know that the result of that scalar multiplication. You don't even need to know how that space looks like. And if you define that sort of multiplication and you perform all that thing that we did previously, you will get kernelized SVM, and you will be able to separate points that are linearly inseparable. There are many sorts of kernels. Here are some examples like quadratic kernel, a polynomial kernel, well, RBF, very often used, radial basis function. It's called radial basis function. As you see, a scalar product is calculated quite simply. The space defined by RBF is quite complicated. It's infinite dimensional. So you are using infinite dimensional space, even in some sense, without knowing that. Knowing some kernels, you can generate some new kernels. Here are some formulas that allow you to make from kernels K1 and K2 some new kernels that you can use in your support vector machine. And using these kernels, you might get much more complicated borderlines between the two sets you are trying to separate. Here is an example. So this is an iris data set. You're seeing a linear kernel. It's separating quite poorly. You're seeing RBF kernel. It separates much better. You're seeing polynomial kernel. It separates on its own. So this is basically the case how it works. So with these kernels, you might get much more interesting and much more complicated results. Okay, the rest of this lecture I will skip. It's about training support vector machine with all its kernels.
Out of break time now.
Yeah, we don't have time. That's too bad. But I have mostly said what I wanted. So I hope that everyone now knows what is support vector and what is kernel.
There are 3 questions in chat, so maybe you can answer them after.
Okay, let me check what they are. As I have understand it, SVM we can use only for binary classification, not for multi-classification. Well, basically, support vector machine, as it is implemented, it is a binary classifier. But in sklearn or in some other libraries, you can see SVM that work with few classes. How that works? You are basically using few support vector machines. Each of them is a binary classifier, but then these few vector machines are combined together into one entity to get you the result. It still has some problems in here. So I even have, I guess I have even a picture of that. For example, here are borderlines between two classes given by two support vector machines. And you are trying to classify between, for example, 3 classes or 4 classes and so on. So you are basically doing binary classification, and that may be, I don't know, classification 1 versus all. So for example, first support vector machine tells you it's class 1 or it's some other class. You get it to the second vector machine, it tells you it's class 2 or some other class, and so on. So yes, there are problems because inherently they are binary classifiers, but combine few machines together, you may get something more complicated. Provide sources for learning theory and mathematical details behind machine learning. Yeah, I guess I can provide, but I don't have them at hand. Well, yeah, I will copy and paste that to the chat a little bit later. I think I have a few books somewhere, so I can give references to that. What Python library do you use for data visualization? Where basically I'm using 2 libraries. The library that works very well in these notebooks is Plotly. So I use Plotly for all that fancy plots when I want something 3D and I want to rotate it somehow and so on. That's because for a long time, Google Colab had some problems with matplotlib, and I couldn't use it for some fancy 3D plots. But as a standard in the ML community, I think you can consider matplotlib. It's used by most people, and maybe sometime they will make it, I don't know, it will work better with Google Colab, so maybe we will be able to switch to it. But all these lectures were written at the time that it hadn't all that nice effects. Does fitting in numerical ML problems include calculation of confidence intervals for fitting parameters like in math statistics problems? No, at least these methods that I'm showing to you, it does not include that. So we are constraining our parameters just by means of regularization. So we are adding something to the Lagrangian and basically tuning that parameters to make them fit into some intervals. But we don't calculate confidences. But maybe when you are doing some meta-analysis of your machine learning model, of course, you can employ some sort of statistics and so on. So for example, it's often used when you are performing some sort of A/B testing, for example. So you have 2 machine learning models and you want to compare them in some real cases. So you are basically collecting some statistics and you are calculating some, and you will be really calculating some confidence intervals and so on. But that's basically about assessing the whole machine learning model. So it's not when training machine learning model, as far as I know, at least. Okay. Seems no more.
Can I exploit my right of a co-host and also ask a question?
Yes, please.
So it's more like a practical question. There was like an example of Chihuahua and cookies classification problem. Can we linearly classify it? Can we use support machine vectors for it, or should we use kernels?
I think we should use support vector machines with kernels to classify them because they don't look like linearly separable. That's the first point. The second point, well, when it gets to classifying photos, it gets a little bit complicated. As you might notice, when you work with classical machine learning methods, they are getting a bit worse when you are getting more and more features. So it would be really a problem if you try to feed a photo, the whole photo to the support vector machine. So it may be troublesome. So maybe you will need to construct some more complicated features out of it, and it will work on that features. For example, hog descriptors. So when you calculate some sort of gradients and so on and so forth. So, so you need something more complicated, some more complicated features, and then pass it to support vector machine. And I will definitely expect that it is not linearly separable. So you will need some sort of kernelized version of support vector machine. My personal preference is the RBF kernel. So I use it almost all the time. I use RBF. It really works fine, and it's a really simple kernel.
So the choose of the kernel is more of like your own preference. There's no like more efficient kernel or less efficient kernel.
Well, you can basically check that by cross-validation. So there's no way you can, I don't know, some sort of minimize something to get the best kernel, but you can always use some sort of cross-validation, and you can just test a few kernels and say, well, this kernel worked well, and this one was not very good. So we can just create few machine learning models, so one with linear kernel, with polynomial, with RBF kernel, and then check how do they perform on the validation set, what results do you get, and which one is better.
Okay, thanks. Also want to remind everyone, if someone wants to ask a question vocally, they can raise their hand, and we will give a right to talk.
So I assume now you have 5 minutes coffee break, and then we will return with a lecture about machine learning.
Yes, yes.